All right, welcome back. We are going to go over first problem solving. Okay, so this is a strategy. You can use it or you cannot use it. This is how I tend to do these kinds of problems. Okay, so the first step is to read the problem. Obviously, you need to know what the problem is asking. Okay, the next thing would be to draw a diagram. Okay, this will help you to really understand what is going on, what you're looking at. Okay, the next thing would be to label all your quantities, your knowns, your unknowns. Most of the time I kind of pick that out of maybe a long paragraph and say, oh, okay, that says this. I pick them out and I write them out so I know both known and your unknowns, okay? Then I'll go through my equations and choose one that I'll be using, just like here, okay? So you wanna go through these equations, which one will fit, okay? Then you wanna solve it, and then you can check your answers, okay? Just make sure that you didn't make any hiccups, any mistakes, okay? So we wanna look at free-falling objects, okay? And in these free-falling objects, we are assuming that there's no air resistance or drag. Okay, so in physics, we do a lot of what we call hand waving, and we say, oh, we're just gonna, ignore the air resistance or any kind of resistance, friction. We ignore that a lot of times. And it turns out to be a pretty good estimation, even though we are ignoring these other things, okay? So we're only going to be concentrating on what we call G, which is our free fall acceleration, as you can see here. Okay, our G is going to be 9.8 meters per second squared. And the way we kind of define our G, we say it's going in this direction. Okay, it's a magnitude. And so our acceleration is going to be a negative G. Okay, so our acceleration, when we're asking our acceleration, it's going to be negative G. Okay, because again, our G is just some kind of magnitude, just a number. It's a scalar, if you may. Okay, and so it's going to be in our y direction or our vertical direction only. Okay, and so our equations of motion, as you see here, will change a little bit. We're not merely just looking in the horizontal direction. We are now just looking in the vertical direction, which really just changes our x to a y, okay, as you can see here. Okay, so these are now our equations of motions for free-falling objects. These subscripts aren't super necessary. It's just here to remind you that it is only in the y direction. Okay, so they're really, again, not super necessary, but just make them, known that you may encounter that, may see that in the textbook, or maybe not, okay? Another thing you can notice about these equations is that instead of putting an A in there, we actually have substituted in our negative G, okay? So normally we have, say for this equation, we normally have V equals V naught plus AT. Okay, so plus A. Now we have plugged in our minus G for that. Okay, so just remember that it's already taken care of in these equations. So don't try to add another negative, and then you kind of might get, all messed up if you try to add multiple negatives in there. Okay, so just watch out for that. If it's in this form already, if it's already got a G in there and a minus sign, you're golden, you're good to go. Okay, so I want to give you guys a couple of examples, okay, to kind of explain what's going on in free fall. So say I throw a tennis ball up and I don't want it to be, going parabolically, but this is just to show that there is some change in distance going up and down. Okay, so saying I'm just going up and down. Okay, so I throw my tennis ball up, okay, in my y direction, my positive y direction, and then it falls back down. So it's in free fall this whole time. Okay, so what is happening to the acceleration? Okay, so in this case, my tennis ball is experiencing acceleration the entire time, but my acceleration is not changing. Okay, the only acceleration that it is experiencing is my gravitational acceleration due to gravity, or my acceleration due to gravity. Okay, so that is the only acceleration that it's experiencing the entire time. So that means that it remains constant. Okay, so my acceleration is not changing. It's the same the entire way. Okay, now if I have the same scenario, throw it up and it comes back down. Okay, as it's traveling through the air, what is its speed doing? Okay, is the speed remaining constant? Is it increasing? Is it decreasing? Is it decreasing then increasing? Is it increasing then decreasing? Okay, think about that for a second. If I have my G, again, constant in this direction, what is my speed doing? Kind of think about it in the way, what is that ball doing? Okay, so I threw it up. So it has some initial velocity, right, going up. Okay, then as it starts to hit its peak, what is that velocity there? That velocity goes to 0, right, at some point, and it turns around, as in it comes back down. So it goes up, whoops, it goes up, then it comes back down, right? Okay, so the whole time as it is moving up, is it increasing or decreasing? It's decreasing, right? Because it's eventually getting to 0, to its peak point. So it's decreasing, and then as it comes back down, as it falls back down, it starts increasing speed again. Okay, so it's increasing. So it decreases, then increases. Okay, so let's keep that. Let me make sure that I don't use way too much time here. Okay, so let me go over and let's start with an example. Okay, so this is an example from the textbook that I've given you guys. Example 2.14. Okay, so we have a person standing on the edge of a cliff, throws a rock straight up. Okay, so I'm gonna draw this as we go. So the rock straight up with some velocity equals 13.0 meters per second. The rock misses the edge of the cliff, so say this is the edge, okay, and it falls back down to earth. Okay, we want to calculate the position and velocity at all 3 of these times. Okay, now if you notice what I'm doing while I'm talking and reading this question, I start to point out key words, key numbers, key phrases. That way I know what I'm doing. Okay, so this is kind of my thought process when I solve problems. Okay, so, all right, we want to know, let me redo this for myself, calculate the position and the velocity of the rocks. So we have T1 equals 1 second. We'll say T2 equals 2 seconds, and T3 equals 3 seconds. Okay, and we're neglecting air resistance like we do a lot of times in physics. Okay, so we are on Earth, so we are going to also say that our acceleration is due to gravity. Okay, so it's going to be minus g, which we know as 9.8 meters per second squared. Okay, all right. So our first step, calculate the position. Okay, so I am going to go to here. That's what I want to do. And look at my equations. Okay, so if I'm looking for, let's see here. We do it kind of side by side. That way we can look at the equations and look at our questions. Oops. Okay, there we go. Sorry. It's going to bother me. Okay. So we want our position and velocity at each of these times. So first thing is position. So we can say our initial position, x, or I'm sorry, y, y, initial is 0 meters. Okay, so we can use our second equation here, our delta y equals v naught t plus a, nope, plus, oh Lord. Okay. I don't know why this pin doesn't want to work properly now. Okay, 1/2 a t squared, right? Right. Okay. Or if we plug in our minus g, it would be v naught t minus 1/2 g t squared. Okay, so that's the first equation that we want to use when we're looking at our positions. Okay, so given that our y naught is 0, I can just make this y, because this is typically y minus y naught, and if that goes to 0, then it's just y, right? Okay, so we have our y, which is our position, equals v naught, which is our initial velocity as 13.0 meters per second, times our first time, which is going to be 1 second, minus 1/2 times g. Remember, our g is just the 9.8 meters per second squared, times t squared, 1 second squared. Okay, so using calculator, we can solve for this. Half of 9.8 is what? 4.9. Oops. I'm getting mixed up with my units here. Okay. Because remember, we're looking at a distance, so it's just in meters. Okay. So now 13 minus 4.9 is 8.1. Okay. So that is our distance in our first second. Okay. Now, if we want to look at our position, our position in our first second. If we want to look at our position in our second, so when t equals 2, I will do the same thing. Y equals 13.0 meters per second times 2 seconds now, minus 1/2 9.8 meters per second squared, times 2 seconds squared. Okay, so 13 times 2, 26 meters, minus, we have a 2 squared times 9.8 times 1/2, 19.6 meters. So 26 minus 19.6 is going to give us 6.4 meters. Okay. I'll move over here. We'll want to do our third second. Guess we can call these y1, y2, and y3. I'll make it more clear for us. We have 13.0 meters per second times 3 seconds. Sorry, my handwriting is getting real sloppy. I don't know why. This pen doesn't like me. 9.8 meters per second squared times 3 seconds squared. Okay. I'll do that in your calculator. Make sure that's right. All right, so I get negative 5.1 meters. Okay, so notice one thing right off the bat. We have a positive position, and then we have a negative position. Okay, now this makes sense. If you remember from the problem, it says that the rock was thrown up and then it missed the edge of the cliff, so it will go back down. And if I'm saying that this, where I start throwing my rock, is y naught equals 0, then I will eventually get some negative value for my position. Okay? All right. So I'm going to, let's see, move this down because we're going to need some more space here. Okay, to really quickly calculate my velocities now. So now I want to know, what are my velocities? So let's go back over here. And we know our initial velocity. Okay. Yeah, we know our initial velocity. We know our change in y. Okay. So we could use this last equation. Okay. We could also use the first equation, I guess, depending on which one you would prefer. Okay, so let's see. Trying to see which one I used in my notes. I feel like let's see. Okay, I'm going to use this last equation, equation 3. Okay, so my last equation is v squared minus v naught squared minus 2, equals, let's start this over. V squared equals v naught squared minus 2g delta y. Okay. So, you zoom in. So for my first velocity at time t equals 1, I have my initial velocity, which is 13.0 meters per second. And this guy gets squared. minus 2 times 9.8 meters per second squared times my delta y. Okay, so my delta y, remember, is going to be my initial, my final minus initial. So my final in this case, if you could read that, is 8.1 meters, and my initial is 0. Okay, so using a calculator, 13 times 13 is 169 meters squared per second squared, since these units also get squared. Okay, minus 2 times 9.8 times 8.1 minus 158.76 meters squared per second squared. Okay, subtract those two numbers, you get 10.24. Okay, and remember this is v1 squared, so we want to square root both sides. Okay, so we get v1 equals the square root of 10.24, which is about 3.2 meters per second. Okay, and when we take the square root of a number, remember that you get a negative and a positive. So we'll have to make sure that we get the right value. Is it positive or is it negative? Okay, that is going to be looking at our diagram. Okay, and as we look here, we can see that our velocity is in the positive direction, so we will take the positive here. Okay. All right. Let's see. 2.15. Okay, I think I am going to stop there and continue in another video. So you can calculate the other velocities. It'll be the exact same procedure as this one. Okay? All right.